Welcome to this lesson on gamma decay, one of the three major types of radioactive decay. Gamma decay involves the emission of high-energy electromagnetic radiation from atomic nuclei. This process is fundamentally different from alpha and beta decay, as it doesn't change the composition of the nucleus itself. Gamma decay is the emission of high-energy photons from an excited atomic nucleus. What makes this unique is that unlike alpha and beta decay, gamma decay does not change the number of protons or neutrons in the nucleus. The nucleus simply releases excess energy in the form of electromagnetic radiation while maintaining its identity as the same element. Let's examine the key characteristics of gamma radiation. First, it's represented by the Greek letter gamma. Gamma rays have zero charge, meaning they carry no electrical charge. They also have zero mass, as they are pure energy in the form of photons. Finally, gamma rays are electromagnetic waves, belonging to the same family as visible light, but with much higher energy and shorter wavelengths. The general equation for gamma decay shows an excited nucleus, represented by X* with mass number A and atomic number Z, transitioning to its ground state. The nucleus releases a gamma ray photon while retaining the same mass number A and atomic number Z. The asterisk indicates that the nucleus is in an excited, higher energy state before the decay occurs. A classic example is cobalt-60. When cobalt-60 is in an excited state, it undergoes gamma decay to reach its ground state. The equation shows cobalt-60*, with mass number 60 and atomic number 27, decaying to regular cobalt-60 plus a gamma ray. Notice that both the mass number and atomic number remain unchanged, confirming that the element stays the same. Gamma rays carry significant energy, typically ranging from 10 kV to 10 MeV. They have extremely short wavelengths, measured in picometers. Gamma rays possess the highest penetration power among all types of radioactive decay, easily passing through paper, aluminum, and even human tissue. To shield against gamma radiation, dense materials like lead or thick concrete walls are required. Gamma decay typically occurs after other nuclear processes. When a nucleus undergoes alpha or beta decay, it often ends up in an excited, high-energy state. Nuclear reactions can also leave nuclei with excess energy. These excited nuclei then release this extra energy by transitioning to a lower, more stable energy state through gamma emission. This is why gamma radiation often accompanies alpha and beta decay. Gamma radiation has numerous practical applications. In medicine, it's used for diagnostic imaging and targeted cancer treatment through radiation therapy. The high penetration power makes it ideal for sterilizing food products and medical equipment without damaging them. In industry, gamma rays are used in radiography to inspect welds, detect flaws in materials, and ensure structural integrity of critical components.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.